Welcome back, everyone. So far in this unit, we have explored the deeper theoretical side of vibrational spectroscopy. We have discussed molecular vibrations, stretching and bending motions, Hooke's law, vibrational progressions, and Dislandres table, and the Planck-Condon principle. We examined how quantum mechanics governs molecular spectra and how wave functions overlap controls spectral intensity. But today we are going to pivot back toward something extremely practical, something that chemists and physicists use every single day in a real laboratories. Today we are going to discuss group frequencies. So when you first look at the IR spectrum of the large organic molecule, the spectrum can seem overwhelming. There may be dozens or even hundreds of peaks. At the first glance, it looks chaotic. A dense forest of absorption spreads across the wave number axis. But thankfully, spectroscopy has a beautiful hidden order. Certain functional groups consistently absorb infrared radiation within characteristic frequency ranges. These characteristic absorptions allow us to identify functional groups almost instantly. A group frequency is the characteristic vibrational frequency associated with a specific functional group. For example, carbonyl group, hydroxyl group, nitrile group, amino group, and many others. For instance, a carbonyl C double bond O typically absorb near 1700 centimeter inverse, and oxygen hydrogen bond stretch often appears around 3200 to 3600 centimeter inverse. A nitrile carbon triple bond nitrogen group usually absorb near 2250 centimeter inverse. This characteristic frequency act almost like molecular fingerprints. This is why IR spectroscopy is such a powerful analytical technique. By simply examining the absorption bands, we can quickly determine what functional groups are present, what types of bonds exist, and sometimes even details about the molecular environment. Now, here is an important question. Why do these frequencies remain relatively constant across different molecules? Why does a carbonyl group absorb near the same frequency in many compounds? The answer lies in localized nature of the vibration. Many functional groups vibrate somewhat independently of the rest of the molecule. The stretching vibration mainly depends on the atoms directly involved in the bond and the strength of that bond. As we learned earlier through Hooke's law, vibrational frequency depends primarily on two things: bond strength and reduced mass. Remember, the proportionality phi is directly proportional to square root of k by mu, where k is a force constant or bond stiffness and mu is the reduced mass of the bonded atoms. This gives us two major principles. Stronger bonds vibrate at higher frequencies and heavier atoms vibrate at lower frequencies. But real molecules are not isolated springs floated in a space. Every functional group exists within a larger molecular environment, and this environment can influence the vibrational frequency significantly. This brings us to a critical concept: vibrational frequency shift. Environmental effects on vibrational frequency. Even though group frequencies are characteristic, they are not perfectly fixed. They can shift depending upon the surrounding molecular environment. And understanding this shift is essential for accurate spectral interpretation. Today, we will examine four major factors that influence vibrational frequencies: bond order, conjugation and resonance, hydrogen bonding, and substituent effects. So let us examine each factor carefully. The first factor is bond order. This is the most direct application of Hooke's law. As the bond order increases, bond strength increases. A stronger bond behaves like a stiffer spring, and stiffer springs vibrate at higher frequencies. For example, a carbon-carbon single bond is relatively weak. Carbon-carbon double bond is stronger, and carbon-carbon triple bond is even stronger. As a result, carbon-carbon single bond absorbs at lower frequencies, carbon-carbon double bond absorbs at intermediate frequencies, and carbon-carbon triple bond absorb at higher frequencies. For example, typical carbon-carbon single bond absorb ranges are 1200 centimeter inverse or lower. For carbon double bond carbon, it is about 1650 centimeter inverse, and for carbon triple bond carbon, it is near about 2100 to 2260 centimeter inverse. The same trend applies to many other bond systems. Greater bond order means greater force constant. Greater force constant means higher vibrational frequency. Now let us move to second factor, conjugation and resonance. This effect is extremely important in organic spectroscopy. Consider a normal carbonyl group C double bond O. A typical isolated carbonyl absorbs near 1715 centimeter inverse. But what happens if the carbonyl becomes conjugated with a carbon-carbon double bond? The pi electrons become delocalized across the conjugated system. This electron delocalization reduces pure double bond character of the carbonyl bond. In other words, the bond becomes slightly weaker. And what happens when a bond weakens? Its vibrational frequency decreases. Therefore, conjugation lowers the carbonyl stretching frequency. Instead of 1715 centimeter inverse, the absorption may shift down to 1680 centimeter inverse or even lower. You can think of resonance as a spreading out the electron density. The bond is no longer a perfectly localized double bond. Its effective bond order decreases slightly. This weakens the restoring force during vibration, and weaker restoring force means lower vibrational frequency. Now let us discuss one of the most important effects in IR spectroscopy, hydrogen bonding. This effect is especially important for alcohols, carboxylic acids, phenols, and amines. Suppose we examine oxygen-hydrogen bond in an alcohol. Without hydrogen bonding, oxygen-hydrogen stretching vibration appears relatively sharp. But when hydrogen bonding occurs, the hydrogen atom becomes partially attracted to another electronegative atom nearby. This interaction pulls electron density away from the original oxygen-hydrogen bond. As a result, oxygen-hydrogen bond becomes longer and weaker. And once again, a weaker bond vibrates at a lower frequency. Therefore, hydrogen bonding shifts the absorption band toward lower wave numbers. But hydrogen bonding does something else as well. It causes the absorption peak to become extremely broad. Why? Because different molecules experience slightly different hydrogen bond strengths. This creates distribution of vibrational energy. Instead of one sharp frequency, we observe broad absorption regions. This is why oxygen hydrogen stretching absorption often appear as a broad bands between 3200 to 3600 centimeter inverse. Finally, let us discuss the substituent effect. The neighboring atoms attached to a bond can strongly influence electron density. Suppose we place an electron withdrawing group near a vibrating bond. For example, a halogen atom, because halogens are highly electronegative, they pull electron density away through inductive effects. This alters the force constant of nearby bonds. Depending on the exact electronic interactions, the vibrational frequency may either increases or decreases. Some substituents strengthen the bond, others weaken it. Importance in spectroscopy is not only identifying the functional groups, it is also revealing information about the electronic structure, molecular environment, and intermolecular interactions. A careful spectroscopist can learn an enormous amount from even small shift in vibrational frequency. Group frequencies are the foundation of practical IR spectroscopy. They allow chemists to identify unknown compounds, confirm synthesized molecules, detect impurities, and analyze molecular interaction. Instead of memorizing isolated peaks, understanding the factors that shift frequencies allows you to interpret spectra logically. You begin reading the molecule's electronic and structural environment directly from the spectrum. Let us summarize today's lecture. We learn certain functional groups absorb infrared radiation at characteristic frequencies known as a group frequencies. These frequencies depend primarily on bond strength and atomic mass. However, the molecular environment can shift these frequencies. Four major factors influence the vibrational frequency: bond order, conjugation, and resonance, hydrogen bonding, and substituent effects. Understanding these effects allows us to interpret IR spectra much more intelligently and accurately. In our next lecture, we will move from spectroscopy theory into instrumentation. We will examine the actual instruments used to record IR spectra and understand how spectrometers detect molecular vibrations experimentally. Thank you for watching, and I will see you in the next lecture. Thank you.